Thanks, Matt. So like Matt said, I'm Jason Lee from Los Alamos, and I've been working on making ZFS faster by accelerating ZFS features. So I would like to begin by giving a quick background about the lab and why we care about ZFS. So for those who haven't watched Oppenheimer, the lab is a scientific research institute, and we do a lot of science, from high energy physics to chemistry, biology, astrophysics, climatology, tons of stuff. And a lot of the science is done through simulations with scientific applications, which pump out tons and tons of data. And by tons and tons of data, I don't mean a couple hundred gigs or a couple of terabytes. I mean terabytes per second. And due to the sheer volume of data that we have, we will inevitably suffer errors from bit rot to hardware going down, anything. And to combat this, we need ways to first detect errors and then fix them. Fortunately, ZFS comes built in checksums and erasure coding, which allows us to detect them and fix them. ZFS also contains a lot of other built-in features like mirroring, snapshotting, compression, and dedupe that might be useful in the future. In particular, compression will become far more important to the lab for our next generation of supercomputers. So here's a high-level diagram of what the lab's supercomputer architecture looks like. On the left-hand side of this diagram, we have a bunch of compute nodes which will be running scientific applications, and they will be pumping out tons and tons of data that is destined to land on the right-hand side of this diagram on Lustre, backed by hundreds of petabytes of hard drives. These hard drives in aggregate are able to ingest data at about 1.2 terabytes a second. However, despite how big that number is, it's not quite fast enough for what the lab needs. Scientific applications are intended to perform science, not perform I/O. So instead of writing directly to our lusters, hard drive back lusters, we instead land data on an intermediate stage called the burst buffer layer, which is about 10 petabytes or so of flash, which is able to ingest data at 3.2 terabytes a second, which is sufficient for our purposes. Once data is landed, the scientific applications are able to continue doing their science while the data is streamed out to the hard drives at a slower rate in parallel, thus allowing us to do more science. So for our next generation of supercomputers and their parallel file systems, the plan is to remove the burst buffer layer and have these scientific applications write directly to NVMe SSD enclosures that, as shown in the big circle on the right-hand side. So due to the economics of flash, we simply can't buy nearly as much flash as we can hard drives. So the total capacity of these enclosures will be somewhat smaller than what we currently have. In addition to less space, these flash enclosures will not be dedicated to writing data. For supercomputers to write data too. Instead, they will also be shared amongst others file system storage stacks for various purposes, reducing the amount of data that scientific applications have available to them further. Additionally, for our next generation of supercomputers, we don't expect the scientific applications to write any less data. If anything, they'll write the same amount of data or even more, meaning we're trying to fit even more data on less space. So for our next generation of supercomputers, we will have to use compression. There's no doubt about it. So for the first step of this project, Brian Atkinson, sitting somewhere over there, benchmarked what happens when we move ZFS to NVMe's. He benchmarked 12 drives backing Z pools in various configurations. So in this graph, there are two sets of 3 lines. The top 3 with the dots and dashes represent the maximum theoretical achievable bandwidth or write bandwidth for these drives. So there are 3 separate lines because as you add erasure coding, the total achievable performance drops. However, as you can see from this graph, the bottom 3 lines, the colored lines, are nowhere close to the theoretical maximums that are achievable. Instead, we're missing somewhere between a third and a half wall performance that these NVMe SSDs are able to write at, which is not good. We're not going to buy drives just to get half of the performance. We want as much performance as we can get. So as it turns out, this issue is caused by a series of mem copies and other memory bandwidth consuming operations that result in these performance lines. So there is a pull request that will fix this issue that Brian's opened called direct.io. I encourage you to look at that. But for my project, I will not be, unfortunately, not be using direct.io. I will be using stock ZFS. So the numbers in the future graphs will be limited to the solid color lines. And in particular, the next graph will zoom into the RAIDZ 2 line on this graph, where our maximum achievable bandwidth is about 12 gigabytes a second. So here's that graph. Once again, the maximum achievable performance of a RAIDZ 2 Z pool with NVMe, that's backed by NVMe, is about 12 gigabytes a second or so. And with that line, we further added more ZFS features that we wanted. So the first thing we added was checksumming, which, as you can see, caused basically no performance loss, which is great. We added a full-blown operation to our pipeline stage, and we basically lost nothing. The next thing we need to enable is compression, because, as I mentioned earlier, we're losing capacity, but writing the same amount of data or more. And the first compression algorithm we tested was LZ4, which is known to be a pretty fast compression algorithm. And it's also the default compression that ZFS uses when you simply turn compression on. And with LZ4, we lose about 70% of performance, which isn't too bad. Compression as in general is a pretty heavyweight operation, but we only lose less than 20%, which is great. However, as it turns out, lab data does not compress sufficiently with LZ4. Lab data is incredibly dense with high entropy, and the algorithm we need to use is gzip, which is known to be quite a bit slower than LZ4. And how slow is it? Well, it turns out when we enable gzip in Z pools backed by NVMe SSDs, our performance just tanks. It goes down to 600 or 700 megabytes a second, as shown by that blue line, which is unacceptable. We can't deploy Z pools with 12 drives and getting only 600 or 700 megabytes a second. That's crazy. So what can we do about this? The path that we went down was to use computational storage, which is a relatively newish technology that's been developed over the past few years. So basically what we want to do is move operations that are computationally expensive to somewhere else off the host, so that we can leave those resources for whatever operations that we actually want to do, like scientific computations. Computational storage can be implemented in a variety of ways, such as with FPGAs, DPUs, computational storage devices, computational storage processors. Some of you might be familiar with the NVIDIA BlueField 2 DPU. The hardware we chose to use was Idetacom's no-load computational storage processor, as shown on the left-hand side. So let me address the QAT-shaped elephant in the room. Doesn't ZFS already support offloading? Yes, it does. But first, QATs mainly are used on Intel machines, as QATs are Intel products. If you want to use a QAT on an AMD machine, you have to buy extra hardware. Second, if you want to use the QAT with ZFS, you have to further reconfigure ZFS and then link it into link the QAT libraries into ZFS, which, as I've been informed by someone in this community, is a no-go. Additionally, when operations are offloaded to QATs, each operation is offloaded independently of each other. So let's say we wanted to enable encryption. So the data first needs to be moved to the QAT, encrypted, and then the result brought back into memory, aka 2 data movements for a single IO. Let's say you want to enable more operations, for example, compression. You take the encrypted data, copy it off out of memory into the QAT, and then bring it back into host memory. Another 2 data movements. And if you want to add checksumming, you have to copy the encrypted compressed data out of memory into the QAT, and then bring back at least the checksum, possibly even the original source data. So basically, there's a lot of data movement for a single IO, which we found to be a bit excessive. So as it turns out, a while back, Intel updated the QAT API to enable this thing they call chaining, which basically allows you to do one data movement and multiple operations in one go. But until those updates are implemented inside ZFS, they're sort of not useful to the ZFS community. So yeah, we can't use them right now. And as you might know, merging things upstream into ZFS might take a while. So even if someone does work on it, it'll take a while to get in. So that's just with the QAT. So what happens if you don't want to use a QAT? What if you're developing your own custom hardware? What if you're a researcher who wants to implement something and run it in a real world setting with ZFS? Well, currently you can't, you just simply can't. There's no infrastructure for adding new accelerators to ZFS. You have to either make your modifications and then push and try to get them merged into the merged upstream, which is unlikely to happen, as you're probably the only person who has access to that hardware, so why would anyone else use your code? Or you have to maintain your own fork of ZFS and then keep it up to date, which is also, quite frankly, painful. So that's where we come in with the ZFS interface for accelerators and the data processing unit services module and associated providers. So at a high level, this is what using ZFS with our change set looks like. So here we have a simple diagram of a single node with data coming in from user space on the left-hand side. So with Z.I.A, with ZFS, with the Z.I.A modifications, the user data will be passed forwards to this entity in the middle called the DPSM, which is sort of like a multiplexer bus type thing that allows you to access accelerators via a standardized API. The data is then forwarded to providers to translate commands into the accelerator specific operations, which eventually lands the data on the accelerators and eventually onto the backend stores. You can have multiple providers going at the same time. Maybe you have a blue field here, a GPU there. You can have multiple providers for a single hardware device. It's however you want to implement providers is up to you. So now let's go a little bit deeper into ZFS. So at a high level, the ZFS write pipeline looks something like this. Data comes in from the ZFS POSIX layer, goes into the data management unit, and lands in the ARC. At some point, the data is flushed out of the ARC, is processed in the Z.I.A pipeline, goes through the VDEV layer, and eventually lands on the backend storage. And inside the Z.I.A layer, there are a bunch of transformations that can occur. The transformations that the lab is interested in are compression, checksumming, RAIDZ, and IO issue. So this is what ZFS looks like with Z.I.A. So what we do is shunt data out of ZFS into a different memory space, well, specifically accelerator memory via the DPSM and providers. There were also some minor modifications to the VDEV layer, but those are implementation details, and I won't go into them here. But basically, data is just shunted out, never comes back into host memory, and eventually lands on the backing drives. So let's first look at the data processing unit services module, or the DPSM. It's a simple kernel module, standalone, and the main purpose for it is to provide two header files, which provide standardized APIs for using computation storage. It provides a user API header and a provider API header. It also acts as a simple registry to keep track of what accelerator is available with which features and exposes them to users, say ZFS. Providers are also kernel modules, and their main purpose is to translate between accelerator APIs and the DPSM's API. They declare what the accelerator provides. So a provider might declare every single functionality in your hardware, or they might declare some subset that you want to expose to your user. That depends on who implements it and how and what they want. We expect that, so providers should generally be implemented by accelerator vendors, as they are most familiar with their accelerators. But if they chose to release their APIs for public consumption, we expect that individuals might want to only expose subsets of accelerator capabilities for whatever purposes they're using the accelerators for. A quick note, providers do not know anything about the users. So in our case, the user is ZFS, but providers should not know anything about ZIOs or ABDs or any ZFS structure. Providers are only there to offload blobs of data. It has no idea what's going on. So implementing providers should be decently easy. All you have to do is include two header files, your accelerator's header file and the DPSM's provider API header file. And with those two, you can define functions that are used to fill in a function structure that the DPSM declares or defines. And you can think of it as analogous to the VFS functions pointer structure. So with that structure, all you have to do is register your provider with the DPSM to let the world know that, hey, this provider exposes these features on this accelerator. And the primary purpose of a provider is to do three things. It provides opaque handles to accelerator memory that allows for users to move data to the accelerator, which then can be used to perform operations on the accelerator. Note that communication with your accelerator is communication protocol agnostic, which we'll get into later. But basically, if you have direct attached drives, you can use operations or function calls that communicate with direct attached drives. If they're not direct attached, you can use function calls that communicate with non-direct attached drives. On the flip side, using a provider as a user is pretty simple as well. All you have to do is include the DPSM's user API, find the provider you want, and then use the functions that the DPSM gives to you. And just as before, using a provider is just getting a reference to accelerator memory, moving your data to the accelerator, and then calling whatever accelerator function you want with your handle. So here is the crux of, or the core of the changes we made to ZFS, the ZFS interface for accelerators, which is a series of modifications to the ZFS write pipeline. It allows for transparent acceleration of CPU and memory intensive operations with accelerators. So the main things we offloaded were compression, checksumming, RAIDZ, and I/O issuing. We also implemented or offloaded decompression because it was kind of low-hanging fruit and it just worked. It was pretty simple. So with Z.I.A. data, user data access is not modified, is not affected in any way that. So if they were writing to their files with some function, they will continue to write to their files with some function. After their data has landed and they want to read it back, they read it back just as they were before without Z.I.A. If they notice any changes whatsoever, it should be that Z.I.A. accelerated their writes. So their I/O just completed much faster than before. ZFS administrators will notice some small changes. Specifically, right now we need to reconfigure ZFS to use Z.I.A. But the expectation is that when ZFS is merged upstream or Z.I.A. is merged upstream, we'll get rid of that requirement. Afterwards, once ZFS has been reconfigured, the administrator will have to select a provider for the Z pool, and then select which stages of their Z pool are offloaded with Z pool set Z.I.A. say compression equals on, which should be pretty simple compared to what all the other configuration options they have to set currently. So earlier I showed you this diagram with the ZIO pipeline stages that the lab wants. So once again, we want compression, checksumming, RAIDZ, and I/O issuing to the backend drive. So this is the effect of what Z.I.A. does to the pipeline. So just as before, data comes in through the ARC, it hits the first stage, compression, and Z.I.A. detects one, compression offloading is enabled, and two, the data has not been offloaded. So the first thing that happens is the data is offloaded, represented by that big green down arrow. And then the compression stage calls the accelerators function, which runs compression, but faster than the software version, and simply returns a status code, which we usually expect to be just okay. The compressed data itself stays in the accelerator. Then ZFS the ZIO will proceed to the next pipeline stage, which is in this case checksumming, where Z.I.A. will detect that one, checksumming is offloaded, and two, the data is already offloaded. So let's just not offload the data again. Let's just use what's already sitting there and compute the checksum. And the same thing happens with RAIDZ and this issuing I/O, eventually causing the data to be landed on the backing drives, having never brought the data back into memory. So note that while this is the set of pipeline stages that the lab will be using, we do not require these stages to be used with Z.I.A. We've made it so that if you say wanted to turn off checksum, you can, and you can simply have compression go straight into RAIDZ, and the compressed data will simply be processed through RAIDZ on the accelerator, never having come back. If you wanted to do something weird, for example, enable checksumming, but not enable offloaded checksumming, you can also do that. When the compressed data hits the checksum stage, it will be brought back into memory, checksummed, and then returned to the accelerator in the RAIDZ stage. So obviously that causes thrashing, but we don't expect that to be your normal mode of operation. So we simply provide the primitives to do it, but we don't tell you how to do it or what you need to do. And if errors are experienced for whatever reason, say you asked for an algorithm that's not supported by your accelerator, but a previous stage did offload the data will be brought back into memory and processed in software. If for whatever reason your data can't be brought back into memory, say with a hardware failure, the entire write pipeline is restarted for that Z.I.A. This is possible due to the copy of the data that's still of the original data that's available in ZFS via Z.I.A. transforms. So you might be wondering how fast or Z.I.A. or how much Z.I.A. can improve performance. Before I get to that, here is a high-level diagram of how we plan to deploy ZFS with Z.I.A. So just as before, the host is on the left-hand side where ZFS runs. Data will come in through ZFS and Z.I.A. get passed to the DPSM and the provider. And instead of writing to direct attached drives, we plan on writing to drives that are over a network, exposed through NVMe over fabrics. So what we want to do, so what the plan is to write to our custom designed enclosures, which are accelerated boxes of flash, which contain NVMe SSDs along with accelerators, and just write to them. So unfortunately, because this was a custom design enclosure, we did not have them ready in time when we collected the numbers. So instead, we developed and benchmarked on a simulation of this, where instead of the enclosure, we simply had two standard servers connected to each other via NVMe over fabrics. Yeah. And this is what we got. So this graph is similar to the one shown earlier. So once again, our maximum performance achievable is about 12 gigabytes a second. And when we enable gzip, performance dropped to 6 or 7 megabytes a second. With Z.I.A. and offloading all of the operations to an accelerator, we achieved that the numbers that we got on that black line, which is about 11 gigabytes a second or so, which is great. We got a 16x speed up. But not only did we move the gzip line upwards, we moved it upwards past LZ4. So we're performing better than LZ4 and compressing better than LZ4, allowing us to use our storage systems better in two separate dimensions. So in addition to offloading the write pipeline, we also offloaded the RAIDZ resilver pipeline. So for those who don't know, RAIDZ is basically comprised of 3 stages in the Z.I.A. pipeline: I/O start, I/O done, and issue I/O. So I/O start is the read part, so we didn't touch that. Issue I/O is the same as the issue I/O stage in the write pipeline, so we just reuse that code. The core of resilver or RAIDZ resilver is done in the I/O done stage, where there's a series of steps that are done to attempt to reconstruct data. And if the first attempt fails, try different combinations of the columns until you successfully reconstruct the data. So all of this was mirrored in Z.I.A. to allow for data to be offloaded and the resilver operation as a whole accelerated. Unfortunately, at the moment, I don't have numbers for you, but this does exist, so feel free to play with it. So I would like to point out 2 very important points about Z.I.A. So first, Z.I.A. does not provide a new set of algorithms. Gzip is gzip is gzip. We are not adding a new enum to say accelerated gzip versus normal software gzip. We did this intentionally because we wanted to make sure that if for whatever reason your accelerator goes away and is not available, we can still read the data off of your drives. Right. And secondly, the existing software implementations of these pipeline stages should not be moved out of ZFS into a software provider, because we need a way to default to an implementation, which is the software implementation. So that there are several arguments for and against moving the code to somewhere else, to a software provider. But for now, the current design is to not move the the code. So having said that, of course, we have a software provider, which so because the software provider is an exemplar implementation of the provider and not the actual operation, such as RAIDZ, we link back into ZFS to get the actual functionality, which real providers should just never do. So this provider offloads data to somewhere outside of ZFS, but it's still, of course, RAM since there's no hardware involved. But the point is that it works. And this provider allows for testing and validation of Z.I.A, which should be useful for CI builds and whatnot. Additionally, recently, the QAT code has been moved into a separate provider, allowing for ZFS to not need reconfiguring or linking with the QAT code. So because the main ZIO pipeline stages that the lab wants are compression and checksumming, the encryption stuff was dropped for now. But if someone would like to take on that part, would happily accept pull requests. And the QAT provider is currently untested, but it does exist. So if anyone wants to play with it, feel free to go to that link and download that branch. So there are a bunch of future directions we could go down. So for example, we could implement more offloads, such as the entire read pipeline or D-RAID resolver, or enable asynchronous offloads, similar to Intel's QAT training, because right now Z.I.A is sort of in lockstep with the ZFS pipeline. The control flow is controlled by ZFS, while the data sort of just sits there waiting for the next operation to be offloaded. But for the moment, the main goal is to try to get Z.I.A upstreamed as soon as possible. And to do that, I need help from the community. Could use more reviews and comments on the PR, could use more testing, could use some help with the build system stuff. If you want to look at the code, there's a pull request open on the ZFS repository. Additionally, the DPSM can also be found on GitHub. And if earlier I mentioned that there were issues with too much bandwidth being consumed by ZFS, currently reducing the achievable throughput when using ZFS with NVMe SSDs. The pull request to fix that can be found here under the direct IO pull request. Cool. So before I get to questions, note that at the end of these slides, or rather, after this slide, there are a series of slides that basically provide a quick demo of how to use Z.I.A with the DPSM. So if you want to play with that, feel free to play with that. And with that, any questions? I think I saw you first.
Yeah, quick question is, so one that sort of problems with offloading accelerators is that if your accelerator is meaning it doesn't match what you can do back in data, they can actually become a bottleneck in hardware acceleration to keep up with the actual amount of data going through.
Sure.
Do you have any ideas or methods to be able to say, all right, well, we can't put everything to be accelerated. We have to put some data through the whole pipeline in order to maintain our data stream, because actually that data accelerator itself has become a bottleneck.
At the moment, we don't. But we have thought about it, but we don't have any solution at the moment.
You mentioned D-RAID resilver as a possible extension. Does that mean you actually have D-RAID rights as existing in your current code, where you can just if you write new D-RAID without do with it, non-resilvering? Is that supported right now? Or
No, just RAIDZ. Someone.
So, yeah, so you get an easy benchmarking, right? It's like 10 times speed up.
Just standard write pipeline.
Okay. So have you done any like other algorithm like RZ4, TZ on STD, ZSTD, and those things?
Good question. So when we started this project, ZSDD hadn't been integrated into ZFS yet. So we just didn't use Z standard. And we also, our hardware supports only accelerated gzip, so we sort of couldn't test accelerated Z standard.
The QAT provider that you have, is that using the new version of QAT or the older one?
The older one, I just moved the code out. I'm not a QAT expert.
You mentioned direct IO patch in this context. Does it mean that we are practically dropping ARC out of the patch completely, or it just drops from compressed ARC to non-compressed ARC, or what's the relation particularly to this, right? I guess we never see compressed data in memory at all. Compressed, are we expected to cache still in ARC, or you're just possibly copying directly to user space?
Could you repeat that?
You mentioned direct IO patch
Right.
in your at the end of the slides. So do you expect it to be preferable way of using Z.I.A without caching data in ARC?
Oh, okay. So no, we don't have a preference. It should work for both.
But compressed data never appears in memory.
Yes.
ARC can be only uncompressed or no ARC at all.
At the moment, I believe we disable our compression.
I think to kind of follow up on that, is there a way to get the compressed data from the accelerator into the ARC? Have you guys looked at that?
Not directly. So obviously we have ways to bring data back into memory in case of accelerator failure, but we don't explicitly do it for the ARC.
So you mentioned that the card is driven forward by the Z.I.A pipeline,
Right.
and the data kind of sits on the card. So if ZFS is too slow there, is there a limit to how much data the card can have in its life?
No, that would be a accelerator specific detail, implementation detail.
And for gzip, do you know, well, gzip is gzip. It turns out it's not always the same. Do you know if it uses the same starting table as the Linux kernel module, or if it uses something more like QAT, which is a different table, so the same block won't compress to the same checksum as the software implementation?
Right. So the idea is that we want the same bits to land no matter if you're using software or hardware. But yes, our hardware actually wrote slightly different bits, but because we computed the checksum on those different bits, it was fine.
Maybe one last question then. Since the accelerator handles actually send the data to the NVMe at the end, how does the interaction with the VDEV layer go to figure out where to put the data on the NVMe?
Right. So we also have some hooks inside the VDEV layer to keep track of stuff inside Z.I.A. But so the data doesn't go to the NVMe. That doesn't land on the NVMe's after, like, across the network. It first the accelerators are also across the network. So, right, it's not like a separate thing. They're sort of right next to each other.
Right, it's the accelerator that actually issues the write to the NVMe, not
Yeah.
ZFS.
Yes. Well, so ZFS does the Z.I.A call, which tells the accelerator to offload it.
Great, thank you very much, Jason.